at SimScale's, responsible for our electromagnetics program. And today we will be diving into something exciting in our webinar, all new electrostatics capabilities in our electromagnetic simulation in SimScale, and of course with partnership of EMWorks. So let's quickly start with meeting our presenters first. First, our guest from EMWorks, Mejdi, is with us. Mejdi is the Senior Application Engineer at EMWorks, and he's an electromagnetic design specialist and with an experience in electrical engineering and applied science. And next, from SimScale, I have my colleague Khairi with me, and he's the application engineer and one of the experts in electromagnetics in SimScale, and also experienced both in CFD and FEA with a background in civil engineering and computational mechanics. So before starting with today's webinar's overview, actually I would like to remind you of the chat section that you should be seeing at the bottom, where you can introduce yourself and also share any comments, thoughts, or especially the questions you might have, and then we'll be answering them at the end of the webinar. But before starting, actually, first, I would like to ask you a question. It will be great if you can share what is your application in electromagnetics, and actually, what is the main problem that you are facing in your daily work that you like to address and find a solution by using electromagnetic simulation. Okay, can we go to next slide, please? And here we see the rundown for today. So we've already started with our welcome, and then we'll continue with a quick introduction both to SimScale and EMWorks, especially for the ones that are new here. And then before getting deeper into the topic of electrostatics, we'll be again covering the general overview of electromagnetics capabilities at SimScale. And after talking about what electrostatics is all about, Khairi will be picking one application that you can address with the electrostatics capabilities here at SimScale. And then he will be jumping directly into a live demo on the platform to give an overview of how to set a simulation there. And then it will be followed by analysis and discussions of the results and some other common applications that could be addressed with electrostatic simulation will be talked about as well. And then we will be leaving that to Mejdi so that he can introduce other analysis types and multiphysics coupling capabilities of EMWorks that are also in our plans as the next steps. And then also we'll be sharing our roadmap, so where we started, what we were focusing on so far, and then where we are planning to go as the next steps. All right, now let's kick things off with a closer look at SimScale's capabilities. So here at SimScale, our mission is actually very clear. It's all about helping engineers innovate faster by making simulation truly accessible. So how do we do that? First of all, it's provided by being a 100% cloud-native simulation platform, which means that you can access that through your web browser. So you don't need to follow any painful setups with remote access or any tricky installations. And of course, also there is no limit regards to simultaneous usage of your team or the number of simulations you'd like to run in parallel, and also the simulation model you want to bring to SimScale. And also SimScale is a single platform where all the physics are streamlined in an intuitive workflow. So you have flow analysis, structural analysis, thermal analysis, and the last but not least, of course, electromagnetic analysis, all in the same environment. So you don't need to switch platforms to utilize different analysis types because it's all right here in one place. And you can seamlessly jump between these analysis types for the same model you have or different models. So now let's also learn more about EMWorks for the ones that are new to our collaboration. EMWorks is one of the top companies that comes into mind within the electromagnetic simulation space with more than 25 years of experience. And their innovative solution actually lies in being the first CAD-embedded electromagnetic simulation provider. And of course, being a single platform with multi-physics solutions is explaining why a collaboration between SimScale and EMWorks was inevitable. And also independent from user background, whether it's whether they're coming from academia or commercial or research, EMWorks has been serving in a variety of industries. Okay, now after this brief introduction, now I'd like to leave it to Javi to talk more about overview of our electromagnetic capabilities, and then he will be starting with today's application.
All right, perfect. Thanks, Noor, for the introduction, and a warm welcome as well from my side to everyone joining us today. So now let's take a look at what the electromagnetic solution that SimScale offers already contains. So a few months ago, we started by releasing the magnetostatic solver. That was our initial step in the electromagnetics journey of enabling it on a cloud solution. Now, magnetostatics deals with approximately constant currents and magnetizations. It can be used for a variety of applications, mentioning here some such as electromagnetic clutches, linear rotational actuators, motors, generators, etc. Some outputs that you might be interested in obtaining from a magnetostatic simulation are, for example, getting insight into the behavior of the magnetic fields, assessing any possibility of core saturations, calculating magnetic forces, and so on. Here on the images, we see some other applications as well. So for example, here we have a NEMA 23 stepper motor, we have a solenoid, and a clutch. Now, after we released magnetostatics, the next solver that was in queue was the time harmonic magnetic solver, which essentially helps us in understanding the behavior and influence of alternating magnetic fields. Think of Faraday's law of induction. In essence, it allows us to focus on dynamic fields that evolve over time. Some of the main applications that are used for time harmonic magnetics, for example, can be transformers, induction heating, wireless power transfer, and so on. Now, what sort of outputs you might be wanting to get from such a simulation? It could be impedance matrices, coupling coefficients, magnetic losses, AC effects, skin, proximity, and so on. All right? So these two analysis types are the one that we have already released on SimScale with our partner EMWorks. Now, let's take a look at today's main topic and a new analysis type, which is the reason why we are here today in this webinar. And that is electrostatics. Now, electrostatics is used for the study of electric fields, charges, and their interaction in electrostatic equilibrium. Now, electrostatics help us in gaining valuable insights on parameters such as the electric fields, the voltage distribution in conductors and insulators, any possibilities of dielectric breakdown, electrostatic discharge, high voltage testing, actuating forces, and so on. The simulation outputs from an electrostatic simulation, of course, relates quite well with the insights that we can gain. We can obtain information on the electric field, the electric displacement, the electric potential. Very important as well is the capacitance matrix and forces and torques. Cool. Now, let's build up on this and let's take a look at an actual real-life scenario application where the use of an electrostatic simulation would be very valuable. And today's application will be high voltage power cables. What are the design challenges and what solutions can SimScale offer when it comes to these? Now, submarine three-phase cables play a crucial role in transferring electrical power between regions separated by bodies of water, supporting essentially the reliable operation of interconnected power grids and enabling the efficient distribution of energy across regions. Now, this could be, for example, from offshore renewable resources such as wind farms, or even on a larger scale to transfer energy between countries. This was something that I wasn't aware of, and in the preparation of the webinar, I found this image that shows all of the essentially laid out submarine cables between the countries, which I found pretty interesting because it really shows the scale of such an operation and the importance that one should put into the design of such a system for reliable and long-lasting operation. As well, here below, we see a cross-section of a submarine cable. We will talk about this a little bit more in detail later once we look at the simulation model. For now, let's get an understanding of what are some of the design challenges that such cables present, and what are the solutions that SimScale offers. Now, for some of these challenges, of course, this is just a short list. There are various other challenges that can be faced in such a design. Some of them are, for example, evaluating the breakdown voltage and the dielectric failures of the cable. So for example, you need to choose a proper insulating material that will be able to withstand very high electric fields to avoid any dielectric breakdown. You might want to investigate electromagnetic compatibilities as well, effects of the cable, to ensure that the marine life around is not really affected. You might want to investigate electric discharge, capacitive inductive effects, take a look into the AC effects, skin and proximity, understand what are the magnetic losses and what amount of heat can be generated from those, etc. Now, in order to address these solutions, let's take a look at what a multiple physics platform such as SimScale can provide to aid in mitigating such design challenges. For example, the electrostatic solver can be used to assess, as mentioned earlier, the dielectric breakdown. We can calculate a safety factor that can help us assess that, calculate capacitance matrices, and so on. We've already covered some of these aspects. On top of that, we also have the magnetic solvers, right? And there you can calculate the losses, calculate inductance resistance matrices, along with impedance, of course, magnetic forces, eddy currents, etc. And to add on all of that, you can use some of SimScale's other solvers, for example, such as a conjugate heat transfer, to take into account heat transfer mechanisms and investigate the temperature of the cables. And then you can also run a finite element analysis to assess the mechanical thermal loads, such as expansion, contraction, and the impact of those on the structural integrity. Cool. Sounds good. Now, let's take a look at the simulation model that we have, and then we jump into the SimScale platform and see some things live in action. So this is the model that we are simulating. It's a small portion of the cable in 3D. It's crucial to simulate it in 3D, actually, mainly because those cables are twisted, right? And as a side note, of course, you can simulate a longer version of the cable. You're not limited to a short, essentially short version of it, because SimScale provides you with the resources to complete such simulations by benefiting from the power of the cloud. So you can simulate a longer version, capture multiple twisting periods, and so on. Now, what does this cable consist of? Well, we have 3 twisted conductors over here supplying a 3-phase AC current. They are confined by a lead sheath material that isolates them from each other, and a choice of an insulating material, such in this case as XLPE, which fills the gap between the insulator and the lead sheath, and of course also the region inside the cable itself. On the outer level, we also have a twisted stainless steel armor bars that provides some mechanical strength, and all of this is wrapped with an insulating material, such as PE. Cool. Now, let us jump into the SimScale platform, give you a little bit of an introduction to what SimScale really is, look at the platform, the workbench, and see some simulation results live in action. So I'll stop sharing now, and I'll jump into a different tab. As you see, SimScale is completely cloud native. You can access SimScale from any browser that you like, from any laptop that you would like to use as well. You don't have to have a proper machine, so it's very different from on-premise solutions in that front, especially when you would like to run very complex and expensive, computationally expensive simulations. So when you navigate to the SimScale website, for example, let's go simscale.com, and then you log in into your account via a username and a password. And then you can navigate to the dashboard. Now, what is this dashboard thinking? The dashboard is essentially the place where you store all of your simulation data. You can organize everything nicely inside folders. These folders can be shared by other teams in your organization. For myself, I really like the folders capabilities because you can organize folders, for example, project A for customer A, project B for customer B, and then you always have access to those, not only for yourself, but also if some other team members would like to find some data, all of this data is stored here. Some questions that we get quite a lot, especially when talking about this, is what is the storage limit that we have on your cloud service? And the answer to this is you have unlimited storage capacity on SimScale. You can have hundreds and hundreds of projects, and you wouldn't have to pay anything for storage. What we also do is that we also take care of the heavy lifting. So we handle all of the infrastructure from our side. We essentially When you run a simulation, this simulation is being fired off to our cloud service, and it's being run on a suitable machine that provides you with sufficient memory to run even the complex of cases. All right. That's on the SimScale side and on the fundamentals of our cloud native solution. Now let's jump into the SimScale workbench where we can take a look live at this high voltage three-phase cable. I will start by showing some results, and then we can see how we can set up such a simulation, and then finally summarize these results in the slides. So now I'll navigate to another tab, and where I am now at the moment is I am inside the post-processing environment of SimScale. The pre-processing, the post-processing, all of the other aspects is done in the same software. You don't have to jump between different tools, etc. Inside the post-processor, you have access to various different filters that allows you to extract meaningful results that can aid in your design. For example, let's take a look at the electric field distribution inside the cable. So now we're visualizing the electric field distribution on this cable, and a few things that we can point out right away is that the electric field is properly confined and isolated from the other cables, which is as expected, and we can also see that the electric field is radially symmetric around the cable itself. All of that is good, but something very important that we need to assess is this safe, or is the insulating, the electric strength of the insulating material being exceeded? Now we can answer this question by simply writing a small equation in the post-processor that calculates the safety factor, which in this case we're using the electric field magnitude calculated by the simulation divided by the dielectric strength of the insulating material, which is in this case 21 million volts. Now, I can visualize the areas that could be indicating of a potential dielectric strength by a means, for example, of an isovolume, where here I'm showing values between 0.5 and 1. If the safety factor value is 1, it means that a potential electric failure might occur. Now, luckily, this case is for 120 kilovolts, and we clearly see that the color of the areas is around the green yellowish color, which falls in this region between 0.6 and 0.5, which indicates that this cable is safe from dielectric failure. I will compare this as well to other high voltage levels later as well in the slides. Sounds good. Of course, some other parameters that you can investigate, as mentioned earlier, are the electric displacement field, the electric potential, and so on. Now, let's take a look at how we can set up such a simulation live on SimScale. To start any simulation, you would need to have a 3D CAD model. SimScale works with almost all major CAD providers out there, whether you are using SolidWorks, Autodesk Inventor, Rhino, CATIA, Creo, NX, etc. And you can import the native formats of these CAD tools directly into SimScale. But of course, you can also import generic formats like STEP, ACIS, IGES, etc. After you import your CAD model, you can go ahead and create a simulation. SimScale is a multiple physics platform. It essentially allows you to run simulations either on flow, so whether you're interested in standard flow simulations or conjugate heat transfer where you couple flow and thermal, and assess heat transfer by convection, conduction, and radiation. Or you can run structural simulations to assess the structural integrity, maybe some harmonics and frequency analysis, thermomechanical analysis, and so on. And of course, our newly released solver with our partners in Works, which is our electromagnetic solver, as well as the reason why we are here today. So I'll go ahead now and create a simulation using the electromagnetics solver. I'll call this Electrostatics of a high voltage cable. The first step of creating the simulation is to decide what is the model that you're trying to solve. So at the moment, we have three options. Either you do electrostatics, magnetostatics, or time harmonics. We will be adding more solvers to those. Majdi and Noor will talk about these as well a little bit later in today's webinar. For an electrostatic simulation, or for any simulation that you create on SimScale, we always provide you with a template. We like to call it the simulation tree, which essentially tells you, work your way from top to bottom. Everything that is red indicates that an action needs to be taken, right? So we provide you with the default material library, and we also have plans to improve our materials as well, to have a more extensive material library in the future. For electrostatics, the material setup is really simple. All we have to define is only one parameter, which is the relative electric permittivity of that particular material, right? After we define any material, we can also go ahead then to the boundary conditions, define our potential levels, etc. Let's take a look at the setup of one of the simulations that I have over here. So we see over here all of the materials properly defined. For example, let's take a look at the dielectric or the insulating material, which has a relative electric permittivity around 2.3. One note that I would like to point out here is we really try to make the UI as easy to use as possible. So whether you are an expert in simulations or you're not an expert, we try to make this experience for you as easy as possible. And when you start using SimScale, please also let us know of any feedback that you may have. I'm sure our product team would appreciate it a lot. Cool. Now that's on the materials. And for the boundary condition as well, it's pretty straightforward here. I'm just assigning some voltage levels. In this case, I was assessing a high voltage scenario of 350,000 kilovolts. And if you may wonder why are we studying different voltage levels, it's because depending on the distance that these cables are going to cover, the voltage level is going to change. And of course, there are other parameters as well that could influence this. Sounds good. So now, for example, I can go ahead and run a simulation on this. Let's call it 350 kilovolts, and then we click run. And then, for example, let's say I would like to run another simulation where I test a new insulating material. And maybe it has different material properties. Just for the sake of example right now, I'll change this. And then I can go ahead and run another simulation, and I call it a new insulating. Essentially, the point of all of this is to give you the insight that with SimScale, you are not limited to running simulation in series. You are not limited by the capacity of your computer and what it can take. With SimScale, you can run as many simulations as you want in parallel. So with any design that you have, all of the what-if questions that you might actually end up going through in an extended period of time if you're running it on in series, you can essentially speed up all of this process by running them in parallel. Now, some other outputs, of course, that you can get from an electrostatic simulation is the capacitance matrix, which provides you, in this case, of a 3x3 matrix that gives you the capacitance influences between the cables, etc. All right, now I mentioned that SimScale is a multiple physics platform. We can run various other magnetic simulations. So in this case, as well, I have a time harmonic magnetic simulation where I'm applying 50 Hertz as the frequency. I am interested in various outputs. I'll talk about the results of this as well later in the presentation. But some of the outputs that we can get from here are, of course, for example, the impedance matrix. And you can download this data for further post-processing. You can get information on the induced voltages, the flux linkages, the inductance matrices, coupling coefficients, and so on. Right? Cool. Now, before we head back to the slides, I think there are two very important points as well that I always like to remind our customer base and our interested prospects about. When you start using SimScale, we really don't leave you alone with the tool. You always have access to the SimScale support via the chat functionality here. You can write us any message, hi, I need help in X and Y. And X and Y can be anything. It can be, for example, I need help making my simulation work. I need help in preparing the CAD. Can you check if my results are correct, etc., etc., right? And it's there to make sure that you get the most out of the platform. What you can also do, because everything is on the cloud, it's so easy to share simulation data with colleagues. Essentially, you can write the email of any person that you would like to share it with, specify what access they would like to view. So for example, let's say I'm working on this project. I want Majdi's opinion on it. I don't have to download data, put in some drive or something, and then download, etc. I can just share, type his username, he would receive an email that Khairi has shared the project with him, and then he would be able to view this project live from wherever he is residing, right? So it's very quick and really encourages collaborations between team. You can, of course, share these projects with your customers as well if you would like to show simulation results right away, which is something our customers also do quite a lot. All right. If you have any questions about the simulation results, about SimScale, about the cloud native aspect of it, please write them as well in the chat and we can address them towards the end of the webinar. That being said, now let's go back to the slides, summarize the results, and then see what is coming next for our electromagnetics offering. All right, so going back to the slides now, and starting with the results summary. So over here, I have an assessment of the dielectric breakdown of the insulator material for different voltage scenarios. We already understood why we might play with the voltage for these cables, depending on the operation that's being intended to. So I have three cases here. I have the 120 kilovolts, which we have looked at. And for 150 kilovolts, we see that there are some areas that are slightly getting closer to a safety factor value of 1. As a reminder, a safety factor value of 1 or more indicates that the electric field is exceeding what this insulator material can actually take, right? So for 150 kilovolts, we see that we are still safe. It's around 0.8, but for 300 kilovolts, we see that there is a very, very, very high possibility of the electric breakdown, right? If it's not almost certain, because we see a lot of values, a larger volume area as well that contains safety factor values of above 1. Cool. Now, from another simulation, for example, using the time harmonic magnetic simulation, we can get insights as well on some AC effects, right? So here we clearly see the proximity effect between the cables where the current then have the tendency to move slightly towards the end of the cable. So the overall area where the current flows reduces, which increases the resistance. And on the right-hand side, we see also a summary of the electromagnetic losses. In this case, in particular, they are the ohmic losses of the copper conductors, the twisted copper conductors, the lead sheath material, and then the steel armor. Of course, these are some results for some use cases and so on. And you can try to think of where these results as well can apply to the use cases and applications that you work on. There are a lot of possibilities, and you guys are the experts in the fields that you work on. And I assume it would be quite easy for you to understand essentially how, from those simulations, from the aspects that we're showing today, how can one streamline their design process a little bit more efficiently by incorporating the use of simulations, especially in early design stages. Cool. Now, before I hand over to Majdi, I'll just take you through some other use cases where electrostatics, for example, can be used. Starting with the left one over here, we have a vacuum circuit breaker. This is essentially used in medium to high voltage electrical systems. What it does is that it tries to interrupt and protect electrical circuits from damage. Here you might want to investigate the influence of the air gap, distance between the electrodes, identify potential breakdown areas, again, by means of a safety factor analysis. You have also an arcing horn, and this is used applied in high voltage power transmission lines to protect insulators from arc damage. Also an on-load tap changer, which you can find as well in transformers. It helps in regulating the voltage level without interrupting the load. Other use cases are the three-phase cable, which we talked about extensively today. Some insulators, these are a string insulator used as well in transmission lines. And maybe you might also want to investigate a spark plug as well to calculate the spark strength by assessing different electric field levels and so on. As I mentioned earlier, these are just a subset of applications that we have simulated so far, but there are so many other use cases where electromagnetic simulations can be used for this purpose. And we would be very happy to hear from you after the webinar about some of the use cases that you have and how we can help you with those. Cool. Now I would like to pass over to my colleague Majdi, who will let us know as well about what are the future plans that we have of integrating other solvers. Over to you, Mr.
Thank you, Patty. Thank you, Noor, for the introduction and the presentation. So EMOX is a desktop solution for electromagnetic simulation for electromagnetic applications. So this solution includes, in addition to what you covered as solvers, the time domain magnetics or transients. So as you can see, in the left part of this slide, some motors applications on which you can use the time domain for simulation of motors. So you can apply any excitations. So you can apply sinusoidal, DC, and pulse. So this is allowed by the time domain magnetic simulation. In addition to the transient, we have the RF, which is for antenna and radar applications. So you can use it for S parameter application, for electric field calculations, resonance analysis, and so on. So it can be used for a wide range of applications at high frequency. And this will include also additional solvers, like we move to the next. So the time harmonic electric field calculation. So it's similar to the electrostatic, but in time harmonic. So you can use it for EMI, EMC applications, for dielectric losses. So you cannot compute dielectric losses using the electrostatic, but it's feasible through frequency domain solvers. And this also similar to the electrostatic, so you can compute capacitance, dielectric failures, breakdown voltages, and can be used for applications like cables, bus bars, and so on. This also, these modules or the solvers includes a DC conduction. So these DC conduction solvers or modules can be used to compute current distributions, which will help to evaluate heat, dissipated heat inside your applications like MEMS, fuse, and so on. So this can be used to investigate different like issues related to fuse and MEMS. So you can compute the stress due to the thermal stress due to the applied currents, and this can be ensured through some coupled analysis that we will see shortly. So the coupled analysis helps you to run different applications, and this is an electromagnetic coupling solution. So you can couple your electromagnetic analysis to motion coupling. So this can be this can help you to study your motor applications, eddy current braking systems. So you can run your device, electromechanical device. So you apply speed, you apply force, torque. So the motion of your, for example, eddy current breakers can help you to generate that eddy current losses. So you can compute the eddy current losses, you can compute the torque due to this losses, and also the time response or the deceleration of your braking system. So this is an electrodynamic simulation that can be used for a wide range of applications like motors, eddy current braking, couplers, solenoids, and so on. So it's a mechanical coupling simulation and can be for like steady state motion. So you just apply a constant speed, or you apply some dynamic speed. So you can apply a speed that varies versus time. So you can use the force, torque to generate the time response due to that force and torque. Another side, so you can use the thermal couplet simulation. So the thermal is mainly used to compute the heat due to electromagnetic losses. So you have an electromagnetic device on which you can see losses. These losses includes eddy current losses, DC losses, also core loss. So these losses are generated in transient and time domain simulation or frequency domain simulation, and the thermal solver can help you to compute these losses, this temperature. So you can compute the steady state temperature and the transient temperature. So you can see the variation of the temperature versus time. So here you can see some induction heating applications. So you can use it for induction cooking system, for hardening applications. Also, it is used in other applications like motors and so on. So then you get the temperature generated for different applications. And this temperature can be used in structural analysis or linear static simulation to compute the stress, to compute the mechanical deformation. So you have electromagnetic forces and you have thermal stress. So the software with its coupled capability can help you to evaluate deformation, mechanical deformation due to both electromagnetic losses and forces, the electromagnetic forces. So you have the forces without the need to import any data. So it's an integrated solution. You don't need to export loss, density, or force and use it in a separate tool or on a separate platform to generate these kind of deformations. So automatically using a one or a single study, the software can help you to generate electromagnetic losses, thermal results, and mechanical results. It's a set of inputs. You have a set of inputs, but you don't define these losses. They are automatically transferred to the whether the thermal solver or the linear static solver or motion. So you can have like a combination of these analysis. So you can have an electrothermal structural analysis, you can have motion coupled to thermal, and so on. In addition to these three options, we also provide what's called a circuit simulator. So you can, it's not shown here, but it's available. So you can use the circuit to model your power system, or you connect your, for example, generator. You have a generator and you connect it to a load. So you can analyze, you can compute the current that is circulating inside eventual load. So it's helpful for motor application, generators as well, and for power electronic devices. So you have these kind of flyback transformers, inductors, and so on. And it's important to use a circuit to couple between the system and the physics or the magnetic problem. So you have a more realistic data, more realistic inputs, and more realistic results. So these are like some of the available like modules and so on. Other options like parametric optimization also are offered. So you can run, as Terry mentioned, what if analysis. So you can try different options, different scenarios. So you can parameterize geometrical and simulation variables. So you can, for example, analyze your data versus different maybe input currents versus different changes in geometry, air gaps, and so on. And this is very important to find an optimal design, to find an optimized structure for your applications. These solvers is gonna implement it soon in SimScale, and Noor is gonna show us the roadmap for this.
Yeah, thank you. So right now what we see, or what you see in your screens, is the overview of what became available at SimScale in the last quarter so far, and what we are currently focusing on, and also the near future plans as the next steps, what is coming soon. So given that it being the basis model within electromagnetics, our first release was magnetostatics, as Harry also mentioned a few slides ago. And that was followed by time harmonic magnetics, which also helped with the capabilities of simulating time harmonic excitations. So in both of the models, actually the insights user can get were mainly based on magnetic fields. And with electrostatics, as we've also been discussing today, the result of interest shifts a bit into electric fields as well. And we covered what we've done so far in the green part. As you can see, as highlighted as yellow, those are the features or capabilities we are working on right now. Yeah, as highlighted with yellow, recently we've been working on time-dependent magnetics capabilities to be available in SimScale, and good news is that it will be ready for trial very soon, actually, and it will be followed by thermal coupling capabilities, and that was one of the most requested features we got so far, actually, and most of the questions are around that topic, so we are very excited to address those applications. So with these final notes on the roadmap, actually, we are about to finalize our part of the webinar, but we think that it's your time to also share your points of view regarding by sharing your applications, but also asking your questions. We are looking forward to those. And actually, that's why for the ones that maybe attended the webinar a bit late, because we saw the attendees number increasing, I will be launching a very short poll where I will be again asking about what you are using electromagnetic simulation for. So it's only taking 30 seconds or 1 minute, depending on if you need to type anything. Okay, thank you very much. We already got answers. So now I would say we can jump into Q&A if our guests don't have anything else to add. Okay. Then one question we got was, does the electrostatic solver help to compute electrostatic forces? Who would like to answer?
Yes, yes, it's possible to compute forces. So it's due to the electric field and the charges. So you can use the electrostatic to evaluate forces, especially for example, when you do DC, maybe bus bars. MEMS application, it's important to compute the forces for MEMS application because these forces are the forces that will generate the deformation of the structure that you need for your actuation. So higher forces, more actuation, so you can use the software and the coupled analysis to compute the electrostatic forces and then the deformation in the structure.
Nice.
Yes.
Thanks a lot, Steve. And another topic is about, question is, I use electrostatic simulations in my daily work already, but I run into some memory issues a lot. What are the limits of SimScale when it comes to these issues?
I think that's a great question. I can take it from here. So SimScale provides a cloud-native solution, right? So depending on the analysis tab that you're running, you have access to 192 cores for your ability to run simulations that can be very expensive with a very large mesh size if you're trying to run a very high fidelity simulations. Usually when you run a simulation, we provide you with an automatic selection that we try to understand from your inputs, from your mesh size, what machine would be more suitable for this simulation. We automatically try to select a machine from our cloud service that will be able to handle the memory requirements, the CPU requirements of that simulation. So with our cloud native solution, these limitations on memory and so on should be eliminated because we practically do provide you with unlimited resources. It's very easily scalable as well on that front.
Thank you. And one more question. I'm interested in EMI and EMC analysis of PCBs. Is this also possible with SimScale? And if so, which module should I use?
I can answer this.
Okay.
Yeah, it's possible. Definitely, it's possible. So you can use the electrostatic solver, and EMI EMC is a very important topic. So you can model your PCB components and put some excitation, some voltage, and analyze the electric field distribution across your PCB and see what are your maybe electric field limits, standards that you should not exceed at a certain position level, certain distance from your PCB, and the software can help you to optimize, reduce the electric field radiation, so around your PCB circuit. So it's an important topic. EMI, EMC has been important for PCB or any other applications like bus bars, cables, and so on. Yeah.
Also, thermally and structurally, PSBs are always a topic that we got so many questions on as well. So together with EMI and EMC, of course, it's even more important.
Yeah.
So I think we are already on time as well. But if you have any other questions, please reach out. And also, before actually finalizing, can we go to the next slide, Ari?
Yes.
Thank you. Yeah, before forgetting this. So we are always working on new events and new webinars. And yeah, as we talked about multiple times already, SimScale is a multiple physics platform. So it's not about electromagnetics, but we are trying to really approach as many problems as we can within the engineering space. So these are some upcoming webinars, and it will be great if you are also interested in those. But yeah, if you have any questions, we are always happy to answer. And yeah, we are wishing you happy simulating then. Thank you all. Bye.
Thank you. Have a nice day. And thank you as well for the questions. If there are any questions that we haven't answered, we'll reach back to you to make sure that we answer all of your questions. Thank you for being here, and wish you a nice day.
Thank you, guys.